Okay, so by putting all of this together, how does it look at DDS system which is actually running? So typically it looks like this. So you're essentially empowered in doing pub/sub over a distributed relational information model. You can partition this information model, and you see in this example that I have 3 partitions, each of which with its own relational information model. And again, there is no centralized server storing the information. So information is fully distributed, so no single point of failure. So in this case, let's assume that P is publishing A and B, so topic A and B, and P2 is publishing D, C, and J. And in this case, we have S1, which is subscribing to A and D, and S4, which is subscribing to A. So once A is published, of course, it's distributed to interested party. There is no surprise here. But now, if also B is published, you see that in a sense this change is retained in the global data space. And when someone, in this case a subscriber, comes around that is interested in B, here you see that at the time the coupling comes into play. So the DS is able to distribute changes, or the last change for a specific topic, even if this subscriber wasn't there when it was produced. But even further, even if the publisher that has produced those changes goes away, if another subscriber arrives that is again interested, let's say in B, then if you have properly set the quality of service, is still able to receive this data. So you see that from an architectural perspective, you have the ability of defining a distributed relational model, and then there are a wide set of quality of service that allows you to control time decoupling, real-time properties, etc., etc. So very, very powerful. And then, of course, you have the many-to-many communication, which doesn't come at any surprise. Let's move now at some pretty cool data modeling idioms. And let's start with a singleton topic. So singleton, it's one of the first patterns that you find in any pattern book. And I thought it was good to show you how you can do a single topic in DDS. So that's important, because the problem is that sometimes you want to ensure that for a specific topic there is only one instance that represents a unique and global property. It's pretty trivial to do that in DDS. You just have to define a topic which is keyless. So a topic which doesn't have key, doesn't have instances, or we could say that there is a single instance and thus it's a singleton. Okay, so now that we have warmed up with this singleton topic, let's move to something more interesting, such as ISA relationship. So let's assume that your problem is that of capturing topic refinement, or perhaps incrementally extending an information model. So one way to do this, if you are familiar with relational information modeling, is to exploit the ISA relationship to refine or extend topic. So what you see here is an example in which I have an employee which has a key, which is the social security number, a name and a level, and then I'm refining this concept by introducing an hourly employee and a contract employee, which have additional fields. So how can we represent this in DDS? Well, that's not hard, and actually there are 2 ways of doing that. One approach, which is space efficient and doesn't suffer from update anomalies, is that of making sure that you share between the super and the subclass, okay, the same key, as you see in this example. So you see that essentially the employee, the hourly employee, and the contract employee all have the same key, okay, and then you essentially have each topic simply keeping track of the fields that belong to the specific refinement. So how would you create in this case a full contract employee? Well, by doing essentially a SQL join based on the key of the specific instance. So that's pretty easy, but again, it shows you the design power that DDS gives you. And this is space efficient. Why? Because if you're updating a portion of the object, you don't need to distribute it all. And also does not suffer update anomalies, because essentially essentially updates are always consistent. Now, if we move to the second techniques that you can use to implement ISA, this technique is time efficient, but is not necessarily immune to update anomalies. So in this case, what you do is that in the type refinement or in the topic refinement, you duplicate all the values for the supertype. So this is time efficient because you don't need to do any joins in order to access the fields of the supertype, but can suffer update anomalies because if you change, let's say, the name for a hourly employee in the hourly employee type, then unless you also change it in the associated employee, you create inconsistency in your data, which is an update anomaly. But again, it's a trade-off because in some cases you need to be very fast and you cannot pay the extra cost of having a join, and maybe you choose this technique, or in other case you want to minimize bandwidth and you can use the other one. What matters is that you know about them. So let's look now at topic slicing and what is this problem. So the problem is that as a result typically of traditional data analysis, you might end up with topic that mix relatively stable data with high frequency changing data. Why? Because conceptually you have a topic that should mix those two, but then practically that's no good. And this is no good, especially when the low frequency data is much higher than in terms of dimension or comparable with the high frequency data. So in this case, the solution is to slice the topic, create two topics which share the same keys, and then in this way essentially make sure that you are bandwidth efficient, because whenever you update the high frequency data, that won't require you to send around also the low frequency updated data fields. The challenge is, okay, how can you then reconstruct and have a coherent view of this topic? Well, you can use DDS multi-topics or a DLRL object to do that things. So the other topic slicing technique should be applied to deal with durability. So again, one of the problems of traditional data analysis is that might lead you to design topics which mix fields which have different durability requirement. And depending on the different and relative proportion of the various portion of your topic, this could lead to poor memory, disk, and network utilization. So the solution in this case is to again slice the topic and make sure that you create topic in which attributes have all the same durability requirement, and again you share the same key. As before, you can locally reconstruct the state by either using multi-topics or by using a DLRL object. So topic slicing can also be necessary for dealing with reliability, and as in the previous case, what you would do is to slice the topic to ensure that you have homogeneous fields with the same reliability in different topics sharing the same key. And as you see in this picture, the basic idea is that so you have reliable data fields and best effort data field mixed in the same object, because conceptually that's what your analysis brought you to design. But then since the state management and the efficiency of the reliability protocol can be influenced by the size of a type, then you really always want to minimize the size of a packet that need to be sent reliably. So splitting them makes great sense. And once again, you can locally reconstruct the state by either multi-topic or DLRL objects. So I mentioned several times, multi-topics or DLRL reconstruction. Actually, there are really three techniques that you can deal with topic fragmentation and for actually reconstructing local view when you segmented or fragmented your topics. One is local joins, and what you can do is that locally you can run a SQL query to join different topics into a consistent view. You can use multi-topic, and those are views that are pre-crafted in your application. Or you can use DLRL reconstruction. So in this case, you can map several different fragments into an object which has a specific relevance for your business logic.